The second FRQ in 4 problems that we're going to see on every AP Precalculus exam is about an object launched straight up with an initial velocity of 19.6 meters per second from a height of 58.8 meters. The table below gives 3 data points displaying time after the object is launched in the air in seconds t and height h of t. So after 1 second, the object is that high in the air. After 2 seconds, it's that high in the air. After that seconds, it's that high in the air. So you can see that this guy is, shot up at 58 and then comes down, hits the ground at some point. Okay? Looks like I'm trying to draw a hangman, and that's not what I'm doing. The object can be modeled by the equation. Oh, it's quadratic, like I guessed it would be. Use the given data to write 3 equations that can be used to find the value for constants a, b, and c in the expression for h of t. So a, I, scares me because of artificial intelligence. Use the given data to write 3. Did I say that already? I think I did. So I have to write out 3 equations using this information and using that information. I don't have to solve it. I don't have to find it. I just need to write it out. So if your t and your h of t, one of my equations is h of t is 73.5. So I'm using this information right here. Equals a1 squared plus b times 1 plus c. That's one equation I could use. The other equation I could use is 78.4 equals a2 squared plus b times 2 plus c. And the third equation that I can find is going to be 34.3 equals a5 squared plus b squared plus b times 5 plus c. 3 equations, 1, 2, 3. Check, check, and check, baby. Now let's do the double I. Okay, the double I. Find the values for A, B, and C as decimal approximations. Well, we know that this is a calculator problem, so what I can do is I can run to my calculator and use quadratic regression. Okay, so let's run over there and do just that. All right, quadratic regression, just like any regression, starts with you going to Stat, hitting Edit, and plugging in the values that you had. The one value that we had, well, the 3 x values, or in our case, the t values were 1, 2, and 5. That matched up with 73.5, 78.4, and 34.3, respectively. All right, we need to do a quadratic regression. So Stat again, Calc, and quad reg is number 5. So go down to 5 or hit 5. And usually when we do this, we would go down to Store Regression Equation and save that. I'm going to show you how to do that just in case you've never seen it before. Vars, you go down the Store Reg EQ, go to Vars, Y Vars, Function, Enter. And then what that's going to do once I hit calculate is save that in here. Now, normally I would do that, but when I go back and forth when making these videos, every time I go back and forth, I lose all this information anyway. But that's all right. I'm going to hit calculate, and this gives me exactly what I need. And if I were to use the equation later, there it is. It's a mess, but negative 4.900000 is basically the same thing as negative 4.9. So negative 4.9, 19.6, C is 58.8, and it gives it to us quite nicely. So that's all we have to answer it. We just have to say what A, B, and C is. We don't have to build the equation ourselves. So let's go back and do that. All right, so using quad reg, we were given A equals 70, nope. Okay, so using quad reg, we were given A equals negative 4.9, B equals 19.6, and C equals 58.8. And if your teacher ever had you do any gravity problems, these numbers should look kind of familiar, especially that guy right there. I mean, that guy gave us our height, which is that guy right there. So it all worked out nicely. So that's part A, writing out useless equations, but actually finding the equation that we would need. B is a three-parter, and B part 1 is asking us to use the given data to find the average rate of change from times t equals 1 second to t equals 5 seconds. Now, there's two ways you can handle this. You just came up with an equation. You could use the equation in your calculator to do the math for you. But what I'm going to do is the fact that it gave us t equals 1 and t equals 5, and look, t equals 1 and t equals 5. So the average rate of change is given to you by the formula h of b minus h of a over b minus a. You would be my a, you would be my b. So h of b would be the same as h of 5, which is 34.3. H of a would be the same as h of 1, which is 73.5. And that's going to be over 5 minus 1, so over 4. Now, I'm not going to waste time going to a calculator and trying to find out what that is. I'm just going to wave my hands and tell you right now it's negative 9.8, which just so happens to be, never mind, negative 9.8. Let's just leave it at that. Okay, so that is B part 1, part I. Use the average rate of change found in I to estimate the height of the object at time t equals 3. Well, what the average rate of change does is it says if we were to start somewhere, if we were to go somewhere, how much is this changing per interval? What this is saying is from beginning to end, or at least from 1 to 5, this goes down by 9.8 feet, or what is it, meters? 9.8 meters every second. Okay, so if we're saying, all right, well, let's estimate 3 at 1, at t equals 1, we get 73.5. So if for every second we go down 9.5 or 9.8 meters, let's subtract 9.8 and then 9.8 again. That gets us to 2 and then to 3. And by doing that, we get 53.9. So estimate the height. So 53.9 meters. I probably should have said up here that this is meters per second. Okay, so let's just add another box right there. Look at that. All right, compare the estimate found in 2 to the value given by the model h of 3. So what I need to do is let's go back to our calculator. Let's use the model that we had, the equation that we had, and compare h of 3 to 59.3. And then, all right, so like I said, once I get rid of the calculator, it goes away. So let's type out negative 4.9 x squared. What was it? Plus 19.6 x plus 58.8. Now, we are being asked to compare this guy where x is 3. So I can find out easily where x is 3 or t is 3 by going down the table and getting 73.5, right? Now, how come in the last one we got 73.5, and now for this guy, or for the other one, we had 53.9. Why is it so different? Well, the actual picture that we're dealing with here, and let me hit zoom fit so I can see the actual picture. And if you're wondering, like, where is zoom fit? Zoom 0. The actual picture is this. Now, let me actually go to the window. I don't need negatives because this is a real life problem. So let me get rid of the negatives. Okay, let me get rid of all the negatives. That's the picture that we have. So we shoot off this object. It goes up in the air and then drops down. Okay, it goes up in the air and drops down. That's the actual object that we get. When we did the average rate of change, we just went from here and said, let's go down and let's go down, and here we are. Okay, but what's actually happening is we have something that's parabolic. It's an upside down parabola. So if I were just staring at the numbers when I found the average rate of change, the average rate of change doesn't realize that I'm actually going up and down. It just thinks I'm going down. Okay, so that's why there's a difference between the two. Now, just knowing the problem that I have ahead of time, what I'm also dealing with is if I hit second calculate, or if I hit second table, we start out at 58.8, and exactly at 6 seconds, we hit 0. What does that mean? That's the ground. At 6 seconds, we hit the ground. So I'm just going to use this to help me find part C when I get to part C, but we're going to answer both of those parts by just looking at the picture that I have here. So let's go back and do that. All right, so what I did using the graphing calculator is I found out that the actual picture looks like this. Okay, by finding the average rate of change, it only assumes that that's what we're dealing with. So the way that we're going to describe this is h of 3 is actually equal to 73.5. Okay, so, but the estimate we found was, what was it, 53.9? The difference is because the model is quadratic, and since I'm running out of room, I'm going to say average rate of change doesn't factor that. It doesn't realize that. It just thinks it's a negative slope because you're just using 2 points. All right, so that's the difference between the two. There you have it. Now, what we saw in the picture is going to help us explain part C, which is how the range values of the function should be limited by the context of the problem. Now, the range values, and actually I was thinking it was domain values, but this is the range values. The range is going to be, and actually, you know what? I do need to go back to my calculator and find out what the maximum is. I think it actually might be that, but I might have to just go back there and find out what the maximum is. So I regret everything. Let's go back and do that. All right, I'm going to spare you and not make you watch me type in these values again. If I have to find the maximum, let me go back to window. Let's make this, I believe it was 0. All right, let me spare you and not make you watch me type this out again. Also, I had to fix my window to what I think should be fine. So when I hit graph, yeah, that works out okay. Now, it wants the range values. Okay, so the range values are going to be from 0 all the way up here. So let's hit second calc to find out what my maximum is. So 4 is my maximum. Go to the left, hit enter. For right bound, we're going to go to the right, hit enter again. And the maximum is 1.99999999999. So probably 2. So now that we know that the maximum is 78.4, which happened at 2, we can go back and say that the range is from 0 to 78.4. So let's do that. Ugh, back and forth. It's like me having a conversation with my father who has different political opinions as me. I'm just joking. He doesn't talk to me. That's the maximum, as we found. So the range is, we'll say you're allowed to include 0, and we were allowed to include 78.4 because that represents the height of the object in the sky. The height of the object. So you can't have negatives. And you can't have anything greater than 78.4. Or anything larger than 78.4. All right, so that's why, because you have an object you're shooting into space, you can't go greater than the thing that you get. You can't go to infinity. You can't go to the negatives because that would be underground, which is just silly. So that's problem 2. After this, we get 2 more, and no calculators allowed. Baby, hope this helps.